Hey everybody, today we're going to talk about motion graphs. And we've already talked about two of the three different ways that we can graphically represent the motion of an object. We've done a whole PowerPoint on motion maps, those little dot diagrams or strobe diagrams. We've also talked a good bit about position time graphs or XT graphs. We looked at one of those when we did our buggy lab, and we did a whole bunch of work with that we're going to review in just a second. And finally today we're also going to add in and talk a little bit about velocity time graphs. They're going to be super helpful for us, especially a little bit later when our velocity is changing. Right now they're pretty straightforward because our velocity is constant. Now, let's take just a minute and review what we learned from our buggy lab when it comes to position time graphs. In this video, we're not going to talk about motion maps because we already have a whole separate PowerPoint and video on those motion maps. We're going to focus here mostly on reading XT and VT graphs. Now, with a position time graph, remember that the vertical axis is position, and position is a vector, so the X symbol, X marks the spot for position, that wears a little hat to remind us it's a vector, and the horizontal axis is time. This is why we often refer to this as an XT graph, because you've got the X and the T. Now, the slope of the line on an XT graph, so important. The one thing I want you to remember and immediately pop into your head when you see an XT graph is that the slope equals the velocity, okay? I can't stress how important this is. This is the most important thing to carry forward because you're going to have to keep coming back to this and remembering it. Remember that the slope has two parts to it because the slope and the velocity, it is a vector. It has a magnitude and amount, and that number value gives us the speed, how fast the object is moving. And the sign tells us the direction. So if the sign is positive, like this slope on this graph that we see right here, the object is moving, usually we would say it's moving forward, up, to the right. If the sign were negative, we would say it's moving backward or to the left or down. It all kind of depends on your problem itself, how you're going to say that. If you hear someone snoring, that's my dog in the background, snoring because he's a good boy. The slope, remember when we did the lab, we calculated out rise over run, and we derived this equation right here, our main velocity equation. Velocity is the change in position or the displacement over a period of time. The y-intercept gives us the starting position, and we also derived that second equation right here that I call the position equation that allows us to find where an object is if we know the velocity, the starting position, and how long it's been traveling, the time it's been traveling. Now, we also just want to remember that we are only looking at situations right now of constant velocity. And how do we know when we just look at a graph like this, how do we know if we have constant velocity? Well, our XT graph is going to be linear, all right? A straight line linear graph on a position time graph means constant velocity. And where is the velocity on this graph? It's the slope. The steeper the slope, the higher the velocity. The more shallow or flat the slope is, the lower velocity. Okay, let's practice this a little bit. Now, here I have a position time graph that I have been given, and I have several questions here. I want to know what is my velocity, what direction of motion, and it's asking me forward or backward. What's the displacement from 0 to 0.3 seconds? And then what is the starting position of the object? And if you're given this, you can do it in any order. I'm just going to go right down the list. And remember, where do I find the velocity on an xt graph, a position time graph? The velocity is the slope. So if I'm going to calculate the velocity here, I just need to know the value of the slope. And I can do that by doing that basic slope equation, that rise over run, where you choose 2 points anywhere on the graph. Pick 2 points that are kind of handy for you. And then you just figure out the difference between the vertical and then the difference divided by the difference between the horizontal. Rise over run. The way that this works out for us, this works out that the velocity is going to be equal to the change in the position, that's the rise, divided by the change in time, that's the run part. And in order to calculate that out, I need to choose 2 points on this slope, on this graph. So I'm just going to choose whatever's easiest. Well, the easiest point, starting point, is going to be the origin. And then I just want to, I'm looking for a place where, you know, it really hits. I could go there, but you know what? I think I like this better. I'm just going to go right there. Because at 0.1 second, it's pretty much at 20 centimeters. That gives me nice numbers to use. So I'm going to go ahead and I'm going to use that. So change in position would be my final vertical value minus my initial. So my final value between these 2 points is going to be at this second point, higher up on the linear graph. And so what position am I at? I'm at 20 centimeters. 20 centimeters minus my initial starting position, that's at 0 centimeters, divided by my final time, which is 0.1 seconds, minus my initial time, which is 0 seconds. All right, this simplifies down to 20 centimeters divided by 0.1 seconds. And if I do that quickly on a calculator, that comes out to 200 centimeters per second. That is my velocity. It's okay when you're given a problem like this, unless it asks you the velocity in meters per second, you can leave that in centimeters per second. If I needed meters per second there, I would just move the decimal point 2 points positions to the left, and I would have 2 meters per second. But 200 centimeters per second is fine. Okay, next question, direction of motion, forward or backward. Remember, direction is given by the sign of the slope. Here we have a positive slope. So we are moving forward. Displacement from 0 to 0.3 seconds. Okay, let me mark this. Here is 0 seconds and 0.3 seconds. I'm like right there, okay? And I want to know the displacement. Well, what the heck is displacement? Remember that our definition of displacement is the change in the position. And our symbol is that delta x, change in position. Remember that is equal to the final position minus the initial position. Okay, so what's my final position? If I come over here to 0.3 seconds and I, come up to my dot and then I kind of come over here, I can read that final position at 60 centimeters minus my initial position. Well, that's 0 because I used the origin. 0 seconds at 0 centimeters. And that tells me that my displacement is a total there of 60 centimeters. boxing your answers helps me see what it is that you actually figured out. And finally, what's my starting position? Well, where do I get my starting position? That's going to be that y-intercept. What is the position of the object at time equals 0? And in this case, the position of the object at time equals 0 is 0 centimeters. It's at that starting position. It's at the origin. And that's all there is to it. Typically, the most complicated thing about reading these is simply going to be, calculating the slope out quickly. But once you've done that once or twice, it should be very, very simple for you. Okay, now let's look at a more complicated graph, because so far we've only really looked at objects that have one sort of segment of motion. But sometimes objects, they start, they stop, they go faster, they go slower. They may even change direction, or they may change their position in different ways. And so look at this graph. This is a position time graph, an XT graph with position on the vertical and time on the horizontal. But in this case, we have 6 specific segments of motion, or intervals of motion. Notice that we do have some numbers on here. Each line, vertical line, represents 1 second in time. And then you've got some numbers that are given to you on the vertical axis there as well. So, question number 1, during which intervals was the object traveling in a positive direction? If this is not immediately obvious to you, because you're not remembering the rules here, just stop the video and take a second and, kind of go back and try and figure this out. And then when you're ready, start the video again. Remember, intervals traveling in positive direction. Positive direction means a positive slope. And so which are the intervals where we have a positive slope? Well, first one of those is going to be interval B. Then we're going to have interval D. And that's it. Second question, during which intervals was the object traveling in a negative direction? Negative direction means negative slope. So in which of these segments do I have a negative slope? Really, the only one is F. During which interval was the object resting in a negative location? Okay, now there's 2 kind of tricks here, okay? This word resting, that's very important. That word resting means velocity is equal to 0. And I don't have quite enough to put the hat on. There it is. So velocity equals 0. That means that on a position time graph, if the velocity is 0, the slope is 0, because the velocity is the slope. The slope is the velocity. So where do I have a segment where I have 0 velocity, but the object is sitting there in a negative position or location? That's going to be A. Right here, I have 0 velocity because I have a horizontal line with 0 slope, so 0 velocity. And I'm sitting at -2 meters or whatever. Next question. During which interval was it resting? It says he. I've got mixed pronouns. That's okay. During which interval was it resting in a positive location? Again, ding, ding, ding. It should go off in your head. Resting means no velocity, 0 velocity, horizontal line, 0 slope. In a positive location, this is going to be E. And during which 2 intervals did this object travel at the same speed? Now, how in the world would I know if he's traveling at the same speed? Same speed would equal same slope magnitude. Just the number needs to be the same. The direction doesn't have to be the same. If you look here, you will notice that D is traveling at about 3 meters per second, because I need to come up here and change my color for a second. D here, from here to here, it's 1 second, and it is having a vertical, a rise difference of 3. And the same exact thing here is happening at F. However, D is positive, F is negative. They're going in different directions, but the speed is the same. So you can have an object like this, 2 different intervals of motion, where the magnitude or the speed is the same, but the direction is different. So this would be D and F. Okay, now you try this one. I want you to stop the video here and just so that you can see the graph. And I want you to describe everything that is happening at each step here. So you might, at A, we're sitting still. At B, we're traveling in this direction at this speed, okay? Like, go ahead and give me everything you can tell me about this object's motion at each interval in time. And when you're all done, come on back and we'll go through it together. Okay, now let's kind of go through this fairly quickly. All right, A, at position A, the object sits still for 2 seconds, and it's at the starting line at 0 meters. At 0 meters. For interval B, the object is traveling in the negative direction because we have a negative slope. And it's traveling, if you do the calculation there, at -1 meters per second. So at -1 meters per second, and because it's going in that negative direction, I'm going to say backward, okay? Interval C, now we have a positive slope. So the object's going to change direction. It's going to go forward. And now if you calculate the slope out, it's going to be 2.5 meters per second forward. And it does that for 2 seconds. You can also put how long it's traveling in here. D, now at position D, we have that horizontal slope. That means that the slope is 0, which means the velocity is 0, which means the object is going to sit still. And it's going to sit still for, 5 seconds. And it's sitting at 2 meters position. E, wow, that's a very steep line. E is actually traveling at -4 meters per second. And we know that it's traveling in that negative direction because the slope is negative, so it's moving backward. And it moves backward for 2 seconds, but it's going fast. F, interval F, we are going positive again. Positive, we are 2 meters per second in the forward direction. And doing that for 2 more seconds. G, again, we have a little interval there where we have horizontal slope. So we are sitting still, or you could say zero velocity if you wanted, 0 meters per second. We're going to sit still, and we're only going to sit still there for 2 seconds at, where are we at? -2 meters. And finally, the last interval, H. We are traveling again forward because I have a positive slope, so travel in the positive direction. And it looks like 2 meters per second forward. Now you can add all that together and you could tell a story with numbers, without numbers, using words like faster, slower, however that works out. But I want you to see that you can pull out actual quantitative numerical velocities from each of the segments here just by looking at the slope and calculating the slope, because the slope is the velocity. And with the velocity, you have the speed for every interval and you have the direction it's moving for every interval. Okay, lastly, let's take a look for just a moment here at a slightly different graph. This is a velocity time graph, okay? So a VT graph. And in a VT graph, the velocity is on the vertical axis, time is on the horizontal axis. Remember, our unit for velocity is meters per second, and velocity is a vector, so it wears the little vector hat. And there's some important information here, okay? Right now, the slope of all of our VT graphs is going to be 0. Anytime you have a constant velocity, that means that your velocity is not changing. So for instance, here at 0 seconds, my velocity is 5 meters per second. At 1 second, my velocity is 5 meters per second. At 2 seconds, it's 5 meters per second. My velocity isn't changing, which is always going to generate a horizontal line on a VT graph. So if you have constant velocity, your velocity on the VT graph will look like a horizontal line at some number. If the velocity is positive, it'll be above the 0 axis. If the velocity is negative, it will be down underneath in the negative numbers, but you're always going to have the horizontal. The y-intercept of the line, that y-intercept of the line is right here on this graph. That is going to give you your starting velocity. And here's the big one. This is the one that's very helpful and very, very good. And good. The area under the graph is special on a VT graph. It tells you the displacement. So the area under the graph, that's all of this. What we mean by under the graph is the area between wherever the line is at and the x-axis, the time axis. That is equal to the displacement. So in this case, notice that we have, if I want to know the displacement, delta x, from 0 to 4 seconds, I just need to do the area under the graph. Well, it's a rectangle. It's going to be length times width. My length, let's say, is 4 seconds times, let's say my width is my height there. That's going to be 5 meters per second. Notice that my seconds divide out, and I'm left with 4 times 5, which is 20. And sorry, I'm going to not put my unit way up in the sky. I'm going to put it where it belongs. 20 meters. Boom. So my displacement's 20 meters. The area under the graph is displacement. This becomes critically important later on. We will practice this a lot more. Okay. Last one. This is for you. Pause the video here. See if you can go through and just list all of this out, and then come back and check your answers. Number 1, velocity. You just read it right off the graph. The velocity line, it's 5 meters per second. That's the velocity. Direction of motion, the velocity here is positive. It's a positive 5. So direction of motion here is forward. Initial velocity in this case, that would be right here at the y-intercept. It's 5 meters per second. The velocity is constant, so it never changes here. And finally, that displacement from 0 to 2 seconds. All right, so from 0 to 2 seconds, I didn't draw that very well, but I'm going to take the area right here, okay? And so from 0 to 2 seconds, hold on, I am just doing that quick. From 0 to 2 seconds, I'm going to take length times width, which is equal to 2 seconds, times the 5 meters per second. The seconds divides out, and I get 10 meters. It is positive because that whole area is up above, and both my numbers there are positive numbers. Okay, from 3 to 4 seconds, let's make that one. I'm going to pick some different colors here to make this a little more visible. So from 3 to 4 seconds, that would be here. So that would be this. And from 3 to 4 seconds, again, I'm doing that length times width. Give me just a second here to get my pen back. I'm doing that length times width. The sort of length, or whichever one you want to do as which, I've got 1 second times the 5 meters per second equals 5 meters. And then it's asking me for the whole business from 0 to 4 seconds. So now it wants the whole thing. That's going to be the yellow. And that's going to be 4 length times width, 4 seconds times the 5 meters per second equals 20. And that's how it's done. So right now, you should have a fairly good grasp on motion maps. You should have a good grasp on position time graphs, and you should be working on getting a solid grasp of velocity time graphs. We are going to practice all 3 of these a lot more. Go into your formative now, and you have some questions waiting just for you. Hope you're having a great day. I'll talk to you later. Bye.